All right, guys. Good morning, good afternoon, good evening from wherever you're watching from. So today I'll be talking on a plane stress analysis of a plate using finite elements method. So I did a video concerning this earlier, but I think I have to do a more elaborate explanation for those of us that requested. All right, so first thing I think we have to understand the question. So the question says perform the structural analysis of a thin plate using the plane stress analysis of a finite elements method. So these are the dimensions of the plate, and this is what the plate looks like. So we have the fixed end here and 10 kilonewtons, and it's 15-meter thick. So first of all, the thing you have to do is you have to discretize your member. Yeah. So this is how I've decided to discretize it. This is my node numbers. And as you can see, we have 4 elements. So obviously when you have this, you have 2 degrees of freedom at each node. So that means you'll be having 2 times 5. So you'll be having 10 degrees of freedom in total, right? So your global matrix will eventually be a 10 by 10 matrix. All right, so let me I think these are just the basic things you need to know, and just to see and appreciate what the codes give you. And also, another thing you have to know in plane stress analysis using finite elements method is for element stiffness method, these are normal things you have to define, because for you to get your K, you have to get your B transpose, your D, your B, your T, and A, and they're all well defined here. So they're all well defined here. You can just look them up. This is your D and all that. So let me just jump right into the code. One thing I want you to notice is I intentionally did this. Here so that you will not be confused at any point when I'm trying to explain the code for the analysis of this thin plate. Mind you, it's an FEA method. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is because I have 10 degrees of freedom. And you can see I have X, Y, X, Y, X, Y, X, Y, X, Y. There's a reason for this. So along the line of the video, you will get to see why I have decided to do this. So without further ado, let me just jump right into the code. So like we have earlier established, we have the parameters of the plate. And mind you, when you have a percentage sign, that means you're just trying to comment out something. So I've just commented how the parameters, which is the constant. So I have this given in the question. And also here, I have to what? Define my node coordinates. Obviously, you're telling the code to do something. So you define your coordinates. And here, this is my vector. When you have a square bracket, that means it's a vector or a matrix. So I've defined my constants, I've defined my coordinates, and I'm defining my nodes. Each node has X and Y, right? So these are my nodes. So 0, 0, 0, 125, 75, 65, like that. So I think this is explanatory enough, but let me just share my screen so that you can see. So this is what I mean by my 0, 0 for here, 0, 0, yeah. And this is going to be 0, 125, isn't it? For your X and Y. Pardon my writing. Yeah, so back to the code. When you define your nodes, what you need to do is now to, so now that we've defined our nodes, then we have to then go straight into the code and define other parameters. So we have our elements. Like I said, we divided into 4 elements. So these elements that are divided here is based on the node numbers. So if you, I don't want to be going back and forth, but when you have your plates this way, and you said you divided into 4 elements, and we said this is our node 1, this is our node 2, and this is our node 3, right? So if this is element 1, that means your element 1 that you're seeing over here is having this node number 1, 2, and 3, right? And so this also goes for the other elements. So let's not waste much time regarding that. And also you have to define your global stiffness matrix. So like I said in the earlier part, because we are having 5 nodes and it's a plane stress analysis, just a 2D method of analysis. So we're having 2 degrees of freedom per node, and that's 2 times 10. So this is what this code is defining here. So you have your degrees of freedom 2 times n, where n is your number of nodes. As you can see, n equals number of nodes, isn't it? So 2 times 10 will give you 10 eventually. So now you have to comment out what this code is going to do. So now you're computing your elemental stiffness, because you need your elemental stiffness to assemble your global stiffness. You must remember, there is a relationship between that. When you have your K, which is going to be the summation of your elemental stiffnesses. Pardon my writing. So when you define that, then you go straight into defining those elements. So mind you, you've defined your nodes, you've defined your elements, And now you want to go straight into defining your stiffnesses, isn't it? Yeah. So yeah, this code is going to compute and display the element stiffness matrix and assemble the global stiffness matrix. So what you've done here is you are creating a loop. So let me just see what I can do here. So there is something called a loop in Matlab. If you're familiar with loop, it's more of a, I mean, just like the name implies, it's make you just to solve a repetitive calculation in a very simple way. So it goes through the cycle. So far you can define your cycle. Okay, yeah, you want to run this calculation. I want you to do this same calculation for me, like maybe say 5 times. I want you to do the same calculation for me, let me say 10 times. So you create a loop so that it goes through that thing based on the number of times you specified. So here we have to create a loop to compute our elemental stiffnesses. Remember, we divided the plate into 4 and we are having 4 elements. So we are creating a loop that solves for the elemental stiffness 4 times. So what this for loop, FOR, for loop. So you define the element. This line is defining the element and it's defining the element as element 1. So it's saying you should go for this loop in 4 times. So this is what I mean. So remember that you define your element here already as 1. This is your element 1. I'm sorry. This is your element 1, this is your element 2, this is your element 3, this is your element 4. So you've already defined your elements, right? So after you define your elements, so you're now creating a loop to run the calculation for the elemental stiffnesses, isn't it? So this is what that loop is doing. So for element 1, it's going to run the loop. So this is where the definition comes in. So you say, okay, yeah, for element 1, go into 1. This is a column size. So the size of all the elements. So we're having 4 elements. So it's going to run this loop 4 times. That's what this means. It's going to run this loop 4 times. Okay, so this is index. So there's something called index in Matlab. So it's a way of just let me say storing the information of a particular element. So there's so many ways you can use index, right? Index or indices. There's so many ways you can use it. So for this what's it called? For this our particular problem. So we have this guy, right? This guy, this guy. So we say this is our 1, this is our 2, this is our 3, this is 4, and this is 5. So the only way you can store these guys, this 1, 2, 3, is by indexing it, right? So you create an index to make the code recognize, okay, if you have 1, 2, and 3, this is element 1. If you have 2, 3, and 4, this is element 2. Do you understand? So that is what you've tried to do here. That's what you've tried to do here. Pardon me. So after you've created your index so that it can recognize the element, you then go down to your X. So remember I showed you something at the beginning. Yeah, so where I wrote my X, Y, X, Y, X, Y, X, Y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is where it actually comes into play. So you created your index of the elements. So your X equals to node index 1, your Y equals to node index 2. I know that this doesn't make sense, right? But let me explain. So what this means is you are indexing the node numbers. So we say we have 2 degrees of freedom per node. So how does this recognize these degrees of freedom in terms of X and Y, right? So that is when you now have to index it. So it goes in such a way that, for you to recognize X, it says nodes into index 1. For you to recognize Y, it says nodes into index 2. So that's how it recognizes this element over here. So it sees this as 1, 2, this X and Y. It sees this one too as X and Y. So it goes around like, okay, yeah, I'm here at node 1, and there are 2 degrees of freedom, X and Y, right? So when it's in node 1, it sees that, okay, yeah, this 2 degree of freedom here is going to be X and Y. So instead of just writing something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because of the index, the code recognizes that, okay, fine. When I have this 1 and 2, it is X and Y. X and Y. When I have 3 and 4, it is X and Y. When I have 5 and 6, it is X and Y. I really hope you understand what I'm trying to say. Yeah, so that's a very good way to just make the code recognize what you're trying to do here. So after you've done your index for the element, you do the index for the nodes. Remember, 2 degrees of freedom per node, so X and Y. After that, you then do your area. So don't be confused about this part. I mean, there are so many ways to attain, right? So in finite element analysis, I'm sure you're familiar with this formula when we have A equals to 1, 1, X1, X2, X3, Y1, Y2, and Y3. I'm sure most of us are familiar with this formula. So basically, what this formula does is just to calculate the area of the triangle for that element. So when you have this guy, 1, 2, 3, and when you begin to do your X and Y, X and Y, X and Y, X and Y. So to get the area, you do this calculation. I'm sure most of us are familiar with this calculation. So, but in order to do that, you can also use this poly area So what this is doing is you're defining your area in terms of x and y coordinates. So poly area. So some of us are wondering what's poly area. So it's basically polygon. And let me just bust your head for a while in case you've forgotten. A triangle is also a polygon. Yeah, a triangle is also a polygon. Yeah, so basically, what this code is doing here is writing the area for the triangle. And here, we have to compute our B matrix. Yeah, our B matrix, I mean, it's this long formula here. So we have this in different textbooks as many things, but I think I have it here. And some of us might be familiar with it. Where you have your B matrix equals this. Yeah. So you define your A, like you've told the code to do your area, you've told the code to calculate your B, and your D, which is your elasticity matrix, you've also defined it. So after you've done that, you then find your K element. So this one is what your elemental stiffnesses. Remember, to get your global stiffness, you have to get all the elemental stiffness and then you assemble, isn't it? So then you have your K element equals T times A times B times D times B transpose. Yeah. So after that, you have this, which is to print the elemental stiffnesses. So what this code here is saying is, okay, yeah, after you've computed this, now print these elemental stiffnesses and display them, right? So you get to appreciate all this line of code when I eventually hit the run button. Yeah. So remember, before you can get your element, your global matrix, your global stiffness matrix, rather, pardon me, you have to get your elemental stiffness matrix as well. So you've gotten your elemental stiffness matrix by all these lines of code, isn't it? By all these lines of code. So now for you to assemble the global stiffness matrix, now you don't have to define. Remember the for loop that I told you? Like this loop is a very, very awesome tool because it saves you the time of writing for each element, writing for each code. I mean, imagine you having like 100 division. So without this loop, that means you have to like write each line of code one by one. Yeah. So for you to assemble the global stiffness matrix, you have your for loop. So for this now, you're creating a loop to say, okay, fine, let my I be equals to 1 from 1 to 3. So when you have a column here, just know that it's saying something like, so okay, when you have something like this, there's a column, 3. So that means you're telling the stuff to define elements from 1 to 3. So that'll be 1, 2, 3. When you have, let's say, 1 column 5, for example, that means you're telling the code to give you the numbers from 1 to 5. Well, depending anyways, some of you might want to go far and start getting decimals, but that's another thing. So that means you're saying from 1 to 5, you need the numbers, the integers, 1, 2, 3, 4, and then 5. Yeah, but that one is just by the way anyways. So yeah, so you define your I equals 1 to 3, and you define your J equals 1 to 3. I mean, somebody might ask, why are we having this? The reason is because for each element, I mean, it's for some of us that are familiar, I mean, it's CST method, right? For filling with elemental elements. So that's constant strain triangle. So that is why you're having 3. Because for every triangle, it's called a triangle. So it's going to having 3 sides and 3 nodes. Yeah. So the reason why you're having your I and J is because for each node, you have to degree of freedom. I think that's self-explanation. So after you define this, your I and J, and then for you to put it into rows and column, you then do your index again. I mean, this index is very, very important. Very, very important. So think about it like, okay, yeah, for my X and Y, I need my stuff, my display to be in X and Y. Yeah. So 1, 2, right? X and Y. Isn't it? 3, 4, X and Y. Right? So that's why the index is a very, very powerful tool for you to index your stuff when you have a very line of code, having so many numbers. So it's a way of storing those information so that it doesn't get mixed up. So you define your I to be 1 to 3, and you define your J to be 1 to 3. So it's creating loops for that for all the elements. And after that, it then assembles them. So this is where the assembly comes in. So for your K global matrix, for you to have them in rows and column, the formula then goes into all the analysis that we've done and find a way of adding those elements. So you said, okay, yeah, you want your K global matrix to be in rows and column. So it then comes this way. And then look into the whole code that you've processed. And then add all those elements together. It adds all those elemental stiffnesses together to get your K global matrix. So after that part, I'm trying not to make this video too long, but yeah. So after that part, so you then put your comment. I mean, when you say percentage sign, you're just trying to comment. So it's not a big deal. So you're commenting the display global stiffness matrix. So which is this? So all these ones are just, I mean, normal things to make it easy to read. So now you're commenting that, yeah, the boundary condition. So remember in the diagram, why do I keep going here? Okay. In the diagram, you have something like this. We said this is 1, this is 2, and this is 3, right? And here is fixed, isn't it? We said here is fixed. So for the boundary condition here, I'm sure somebody will ask, why do we have fixed underscore DOF 1, 2, 3, 4? Just like I've earlier explained. You take this one as 1, 2, you take this one as 3, and 4. You take this one as 5, and 6. You take this one as 7, and 8. You take this one as 9, and 10. So if you follow that numbering, you will find out that this node 1 and 2, falls under this guy. 1, 2, 3, 4. I don't know if that makes sense, but I believe it does. So that is the way find a way of defining the fixed nodes in Matlab. So after you've done that, you've told the code out here, these guys are fixed. These nodes are fixed. So, and obviously for you to get the number of nodes that are free, so it's just like normal calculation. So you know the fixed nodes, and you know the number of nodes. So that means you subtract all these guys, all these guys, all these guys, all these guys from your 1, 2, 3, 4, up to 10. So that you can understand what I'm trying to say. So this is what you've done. Where are you? Yeah. So from your question, you know that, okay, yeah, these guys are fixed. So for you to know the ones that are not fixed, that means you subtract this guy from this other guy. So 5, 6, 7, 8, 9, 10 are free. Yeah. So then you come here. So this is what this line of code is doing. So you define your fixed degree of freedoms, and then you're defining your free degree of freedom by saying what? Get the difference. So to get your free degree of freedom, you're setting the difference of the entire column and the fixed degree of freedom. So this one will display the 4 and the 5, 6, 7, 8, 9, 10. So let's not waste more time on this. So yeah, you're defining the nodes, the load that is coming on the plate. So remember from what we have here, we have our nodes. Our load should be 10 kilonewton. And this same principle of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 still applies. Still applies. So F equals 0, degree of freedom, comma 1. So F times 4 minus 1 equals 10 kilonewton. I mean, this is 10 raised to power. That's 10 raised to power 3. That's 10,000. That's 10 kilonewton. Yeah. So somebody might wonder, what's this? So basically, it's saying, okay, yeah, put this force at 2 times 4 minus 1. So 2 times 4 minus 1 is 8 minus 1. That's 7. So it's saying put this force at node 7. Oh, what have I done? Yeah, put this force at 7 and put this force at 2 times 5 minus 1. That's 10 minus 1. That's 9. So what does that mean? Let me go back here. So we have this. So it's saying you should put the force at 7 and 9, right? So 7 and 9 correspond to the x coordinates, isn't it? Because your force is in the x direction, yeah? So it corresponds to the x coordinates of 7 and 9. And these guys fall under node 4 and 5. I believe that makes sense. I think it does make sense, yeah? So after that, you define your boundary condition, you define your load, then you come over to your reduced stiffness matrix and force vector. Yeah. So you comment this one out to say, okay, yeah, I want my reduced K global matrix and I want my K force. Yeah, reduced. So basically, you know that what this reduced is doing is, so from the normal FEA analysis, when you have a boundary condition, depending on what the boundary condition is, yeah, the boundary condition actually has a way of deciding what happens to your stiffness, your global stiffness. So when you're saying this one is fixed, yeah, so that means the nodes associated with this fixed part is going to be 0. And when they are 0, the whole matrix is going to reduce eventually, isn't it? So imagine a situation where you have you're supposed to have 5 nodes and 2 out of the nodes is gone. Yeah, so that means you're left with 3 nodes. And when you're left with 3 nodes, eventually 3 times 2, you'll be left with a 6 by 6 matrix. Yeah, I believe that makes sense. So this K reduce is just trying to sieve out the nodes that have been affected by the boundary condition. So that's basically what that is doing. All right, so moving on. Moving on, we have yeah, so you've commented out this part to display the reduced matrix, and it's going to do that for you. Matlab is generous enough to do that. And yeah, you're saying, okay, yeah, solve for the displacement. Solve for the displacement. So basically, from our relation, which is F equals KU, yeah, F equals KU. It might be U in some text, it might be D in some text, depending, but the point is, we are looking for our displacement, yeah? So our displacement U is going to be F over K, right? Yeah. So F equals KU, and your displacement is going to be F over K. Well, that's just by the way. So after you've already said, okay, yeah, you displayed the reduced matrices, now you solve for your displacement. So this guy here is actually solving for the displacement. And so where you have your free DOF, it's telling you, okay, yeah, there's a degree of freedom here that is free. So this one are associated with the node numbers that are of 1 and 2. Remember what we have in our drawing. So moving on, you've told the code to display Yeah, so you basically define all what is necessary for your input. So now you have your percentage, you're commenting out, okay, yeah, displacement formatted. You've already said, okay, you've given them the information from the previous lines, and then you're saying, okay, f print f, which is to print the node numbers, print the coordinates, print the displacement. When you say f print f, you're just saying, okay, yeah, print this thing in this format. F print f means, okay, yeah, print, but in this format. So this is the format you want it to print it. Print my results, okay, in terms of the node numbers, in terms of the coordinates, in terms of the displacement, yeah, u and v. So this is the format you want it to print it. And this is another loop here. I've explained what loop is. And then end. Very simple. So your line 85, yeah, you're commenting out your stress for each element. So let me just go back to my, okay, yeah, so you know where your stress is, for a plane stress analysis for a template. All this, your sigma x, sigma y, and your tau x, they have value. But other components such as sigma z, where's my marker? But all other components such as sigma z, your tau, um, your tau yz, and your tau xz equals to 0. Yeah, you can just check other literatures to refresh your memory on that. Yeah, so, and you know what your formula is for your principal stress, which is your sigma x plus sigma y over 2 into this long formula. Yeah, so when you know your formula, to put them in code shouldn't be hard. So that is basically what we've done here. So after we've inputted all those guys into our formula, so what we now have to do or start enjoying is to see our display, isn't it? I mean, all these are self-explanatory. So yeah, you're just creating a loop. So what you're creating this loop for is to calculate the stresses for each element. Remember, we have 4 elements, right? So, and I told you earlier that loop is just to perform iterative calculation. Yeah. So what this guy is doing is, okay, fine. For my elements, I want the stress. For my elements, I want the strain. And then print all these things in this format. Yeah, in this format. All right. So that being said, then you calculate for your principal stress for each element. I think I already showed us what the formula is for our refresher. And yeah, another loop is going on here. A for loop is going on here. So it's going to perform the principal stresses for each element and display. And after it's performed that for each element, it's going to now print the results in this format. Yeah. Okay. What else? Yeah. So basically for visuals, you need to see what the form plate is going to look at like. Yeah. But in the real sense, the plate is 15 MMT. The deformation is actually going to be very, very, how will I put it? It's going to be very, very minimal because, okay, think about it. When you have a sheet of paper, your normal A4 paper, a sheet of paper, and you put a force on it, let's say you drop a force on it, right? Against a wall or against the floor. If it drops on it, you're probably not going to see what the deformed shape is like. It's there, right? But it's not going to be visible because it's against a fixed object. I don't know if that makes sense, but I believe it does. Yeah, so the deformation here is very, very minimal because of the plate thickness. Yeah. So what we've done here for visualization's sake is just to increase the scale factor. So that's why you have, okay, yeah, I want my deformed calculation and I want the scale factor of 5,000. So you will get to see all this when I run the analysis. So yeah, you said, okay, I display my x coordinate, display my y, deform node equals to node plus scale factor. So all these ones are just for graphics and visuals. And then you said, okay, yeah, plot the original and deform shape. I mean, you get to appreciate all this when I run the code. Yeah. So you're having a for loop again. I've explained this already. I've explained all these already. Yeah, I've explained all this already. So all these ones are just for visuals, And all these ones too are just for visuals. So basically, like the question I've said, that's the question I've said. Perform the structural analysis of this given plate with this parameter. So that is what the code has actually done for you. So all these lines of code is doing that for you. Yeah. So when I hit my run button now, I'll be having this. But mind you, this red, you have this red dotted line, is exaggerated because of the scale factor we've used. We've used a scale factor of 5,000. It's just for visuals. So in the real sense, it might not be like this. In fact, it's not going to be like this, yeah? But just for visuals. So now we have this. So this is our node 1, node 2, node 3, node 4, node 5, yeah? And now this is what we've said, okay, yeah, I want you to print. Let me just push this up so that you can see. So this is my elemental stiffness. Yeah? For element 1, element 2, 3, 4. Yeah? I mean, this makes sense, right? Because for each element, like I've been saying, for each element, because it's a CST method, constant strain triangle, you have 3 nodes per element. Yeah? You have 3 nodes per element. So when you have 3 nodes per element and 2 degrees of freedom, so that means your matrix, your stiffness matrix for that element is going to be 6 by 6, isn't it? Yeah, 6 by 6. So that is why you see that each of the elemental stiffnesses is a 6 by 6 matrix. Yeah? All right, I think that makes sense, right? And what else? What else? What else? What else? What else? Yeah, element. And this is your global stiffness matrix. So this is just assembling all these guys. Assembling all these guys, taking away the repetitions and all that. And here you have your global matrix, which is a 10 by 10 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. And then this is your reduced stiffness matrix where you do your guys with the boundary conditions, isn't it? So remember, like I said, I mean, I don't even have to explain this. I've explained this clear and clear enough. Yeah, clear and clear enough. And this is your force vectors. Yeah, your force vectors. This is your node 1, 2. Oh, no, sorry, what am I doing? Yeah, this is your first vector. And this is your node numbers. I mean, it's pretty straightforward. And these are your elements, your elemental stress, sigma x, sigma y. And these are your principal stresses. Yeah. So the same process or the same procedure goes for different division. I mean, if you want to have maybe a better or cleaner display, you can just come here and start clicking them one by one. But let me just do this. Okay. Yeah. So I mean, this one is just displaying it in more formatted, but that's just by the way, anyways. Yeah. So I think that's all about that. If you have any questions, just put in the comment section and feel free to ask. If you think you want this file, I can put a link there in the description. Yeah, so thank you. I think by now I've been able to explain what the code has done and the steps involved in writing the code. All right, peace out.